Hello, in this video we will solve for the laminar flow in the plane Poiseuille flow configuration. So first of all, to look at plane Poiseuille flow, we need to draw what this flow looks like. So this is a configuration where the flow is confined between two parallel walls, like this. And I'm going to draw here my axis. So this is going to be the y-axis, and this is going to be the x-axis. But I'm going to draw actually the velocity u, the velocity in the x direction along that axis. And plane Poiseuille flow is the flow in which is driven by a pressure gradient in this direction. So there will be a pressure gradient in this direction, forcing the flow to the right and yielding this sort of parabolic velocity profile. Okay, so to start with this flow, the first thing that we're going to write are the equations and the boundary conditions. So to start with, we're going to write the Navier-Stokes equation. So that equation reads rho times du by dt plus u dot grad u, that's our left hand side, so our inertial terms. And on the right hand side, what we're going to have is a forcing term due to the gradient of pressure plus mu times the Laplacian of the velocity, which is our viscous forces. And this flow is driven by a pressure gradient in the right direction, or in the left direction rather. This is essentially modeled by a volume force, which I'll add here, which is g, and it's carried by the x direction, so ex. Okay, so this is essentially the forcing term that generates this flow. So that's the Navier-Stokes equation, which you know, and this is the additional forcing term that generates the flow. So we have our Navier-Stokes equation. We also need to have the incompressibility constraint. Incompressibility be constraint. So that incompressibility constraint reads divergence of u equals 0. Okay. And last but not least, what we also need to add there is the boundary conditions. So the boundary conditions for this flow, there's only walls in this y direction. So I'm going to say that these are no-slip boundary condition. There is no velocity at my wall, and my wall is located at, I didn't introduce this, but this is going to be 0 here, this is h, and this is then going to be minus h, just to make things well defined. Okay, so that's our setup for plane quad flow. And the first thing that we're going to do is to non-dimensionalize these equations. So the first thing that we're going to do then is the non-dimensionalization. Non-dimensionalization, and to do this we need to introduce some quantities for this non-dimensionalization, and I'm going to introduce my scale for the velocity is going to be capital U, which is just an indicative velocity, times u star, so that's going to be my non-dimensional quantity for the velocity. As far as the position is concerned, I'm going to non-dimensionalize positions, distances, using half the height of this channel, half the separation between these walls. This is a choice. You can also use 2h, which is the complete separation. You could have also introduced 0, define the origin of your axis to be, or your system here to be at here, and so you could have 2h or h here. So these are just complete choices, and they do not impact the result of the calculation. So times x star. For the time, I am going to introduce no new quantity. I'm just going to use my scales for the velocity and for the length to define my time, my characteristic time, h over u. It's an effective time, so times t star. There's my pressure. For my pressure, I'm going to not introduce any new quantity and just introduce rho u squared. as my non-dimensionalization for the pressure. Again, there are different choices possible for the pressure. This is just one of them. And just to make things simpler to write, because I'm going to have some terms coming into the right-hand side, my constant, this forcing term here is a constant, okay? It's just this constant that drives the flow. And so I am going to also non-dimensionalize this constant, not that it matters much, but it's just going to make the equations nicer to look at. So by introducing rho u squared here over h times g star, and this is my non-dimensionalized forcing term here, and this is also of course a constant. It doesn't really matter because all this is a constant, but it's just going to make the equations nicer to look at. Okay, so now that I've introduced this non-dimensionalization, I'm going to take my equations as well as my boundary conditions, and I'm going to non-dimensionalize them. So what I have is, for the Navier-Stokes equation, I'm going to have rho, and then within my parentheses, I'm getting here a u squared over h times du star over dt star, plus another u squared over h u star dot grad star u star. And on my right hand side, my gradient of pressure is non-dimensionalized by rho u squared, so I get rho u squared over h times the gradient, there's a minus sign coming in front of it, times the gradient of the pressure. Everything is non-dimensionalized here. Then here I've got mu times u over h squared coming from my Laplacian operator. Okay, and then for my force term, I'm going to have g, which is non-dimensionalized, so it's rho u squared over h times g star ex. It's carried in the x direction to enable the flow to be driven horizontally here. Okay, so what we see is that on the left hand side I've got rho u squared over h everywhere, so I'm going to divide everything by rho uh over rho u squared over h. And that gives me on the left hand side du star over dt star plus u star dot grad star u star. It's my advection term. There's the rho u squared over h taken out. And then on my right hand side, this simplifies into minus grad star p star. Here I am going to get mu over rho uh, which is 1 over the Reynolds number, if you followed the definition of the Reynolds number earlier. So this is going to be times Laplacian of u star, and this is essentially the same group that I got on the left hand side, and that's how I decided to take this group as a non-dimensionalizing factor for my forcing term. So I'm just getting g star ex. Okay, and by writing this I have introduced the Reynolds number, which is rho h over mu. Okay, so this is my Reynolds number. So I've got my Navier-Stokes equation. This is non-dimensionalized. This is this equation. I can also write down my incompressibility constraint in non-dimensional form, but fortunately for us this doesn't change because these are just terms that are going to be factors that are going to be in front of the divergence of u in non-dimensionalized form. These factors are non-zero, so they can just be simplified. So we are going to get this non-dimensionalized incompressibility constraints, and that's our system. And the boundary conditions are together with, and the boundary conditions, u equals 0, so u star is equal to 0, okay? And this is at y equal plus minus h, so that means that this is going to be at y star equals plus minus 1. Okay, so this is the system that we have to solve. Okay, so to solve for this system, we must first, I think, write these equations in their component form. That's going to help us. And to do this, the first thing that we are going to do is to look at the form that the velocity must take here. So we're looking for the simplest type of flow generated in this configuration, and that's the flow that I've sketched here. So we're going to assume a certain number of hypotheses. So the flow will look like, so hypotheses on the flow. So the flow, first of all, we want a flow that is stationary. There's no need to introduce any temporal complexity here. We need to find something that is analytically calculable. So first of all, the flow is going to be stationary. So we're going to remove all these time derivatives. Second of all, we actually want a one-dimensional flow. We don't want any flow in this y direction. There is no reason to have a flow in the y direction because the driving force is in the x direction. So we can imagine that it's only moving in the x direction. And furthermore, we also can assume that there's no flow in the z transverse direction, because we could just reorient our axis in such a way that the forcing term and the flow directions are aligned. So we also want that flow to be one-dimensional in the direction of forcing. That is where the flow is generated. And the last hypothesis that we will make is that the flow doesn't vary neither in the transverse direction. We will assume that the flow is invariant in that transverse direction, but also it's not varying in the streamwise, in the x direction. Okay, so there's only a variation of the flow in the wall normal in the y direction, because this is essentially a variation that is imposed by the no-slip boundary condition. So the flow is driven in the x direction, so we're only assuming x, a component of the velocity in the x direction, and that component of the velocity in the x direction is only going to vary with the y direction because it's got to go down to 0 due to the no-slip boundary conditions at plus and minus h. So the second thing is flow velocity variations only in the wall normal direction. And these hypotheses lead us to write that the velocity of the flow, and I'm going to write this in non-dimensional form, is essentially a component which is u, right, which only varies with y star, and this is carried by the ex direction. There is no x dependence, no time dependence, no z dependence here, and there is no velocity component in the y direction nor in the z direction. V and w are 0. So once we've got this written down, then we can express these equations, or what remains of these equations, in component form. So first of all, there is no time derivative here, nothing changes with time, so that term goes away. So components in component form. So the first equation gives us for u 0 for the time derivative, then we get u dot grad u, so that's u du by dx, u does not depend on x, plus v du by dy, there's no v, plus w du by dz, there is no w, so that term is also 0, there is no inertia. Then on the right hand side we have minus dp star by dx star, and then plus 1 of the Reynolds number times the Laplacian of u, and u varies with y, so what we get is d2u star by dy star squared. That's this term, and then we're talking about the x direction, so I need to add this g star component. So that's my x direction, okay? Then I need to look at the y direction, okay? So in the y direction, v is 0 all the time. So I've got nothing on the left-hand side. So 0 here, I've got 0 for the inertia. I've got minus dp star times dy star here coming up. And then the viscous term, there's no v, so that term is 0. And that term is 0. And if you want to continue, you can write this down as well for the z direction, and you will get 0, 0 equals minus dp star by dz star plus 0 plus 0. Okay? Then the incompressibility constraint essentially just gives you du by dx equals 0, but u did not depend on x, so that doesn't matter, plus dv by dy equals 0, v 0, so it doesn't matter, plus dw by dz equals 0, it's also 0, so it doesn't matter. So what that means is that our flow, based on this assumption here of a flow moving in the x direction but only varying in the y direction, is an incompressible flow. So I'm not going to write down this equation here, okay? And so these are our equations. So what we can see from this is that, particularly from these two equations here, is that, well, the pressure does not depend on y, does neither depend on y nor on z, and therefore P star is P star of x star, okay? And furthermore, we can rewrite that first equation in this fashion, say that it's dp star by dx star equals 1 over the Reynolds number times d squared u star by dy star squared plus g star. What we see is that this is a function of x star and that the right hand side is a function of y star. In other words, both of these sides are equal to a constant. And what that constant is a gradient of pressure in the x direction. But if you remember what we had here, we just said that, you know, the flow was forced by a constant volume force to the right, in the x direction. That is, in a sense, it's a pressure gradient in the x direction. Okay? So what this tells us is that there's a pressure gradient that is a constant in the x direction. And what we can do is that we can absorb this pressure gradient into g star. And therefore, we can just say that this residual pressure is 0. Okay? So now that we've determined that constant, we can solve for the flow. So this constant that would have appeared here can be absorbed in g star. So what we have is, we can just simply write this as a partial differential equation on y. So it's du star over dy squared equals minus g star times the Reynolds number. In other words, I can solve this right away and say that u star equals minus g star times the Reynolds number over 2 times y star squared plus a constant of integration, k1 times y star plus another constant of integration, k2. And these constants of integrations are going to be determined using the boundary conditions, which are written here. So our boundary conditions tells us that the velocity has to be 0 at plus minus 1. So we're going to write it. At plus 1 I have minus g star re over 2 plus k1 plus k2, and that velocity has to vanish. And the same thing has to happen at minus 1. So at minus 1 I've got minus g star re over 2. That becomes a minus sign here. Minus k1 plus k2 equals 0. And combining these two equations, what I can do is add them up together, and I get and I get minus g star re plus 2k2 equals 0. So that means k2 equals g star re over 2. And I can also subtract them, and if I subtract them I get 2k1 equals 0, that is to say k1 equals 0. So I can replace all that in my velocity, u star, and that becomes g star re over 2 times 1 minus y star squared. And this is the velocity that you have in plane Poiseuille, for the laminar flow in plane Poiseuille. So you can see that it's a parabolic profile, hence this parabola that I drew there, that it goes to 0 at the walls, y equals plus minus 1, so we get these zeros here, and it's maximum for y star equals 0, that is to say in the center line of our channel. Okay, so one thing that one can do from there is, if we want to get back to dimensional quantities, then we can just plug the in dimensional form. So plug all these quantities that we've defined here, as well as the Reynolds number. So in dimensional form, what we get is u over capital U equals my g star, which is here, becomes gh over rho u squared. There's a 2 coming in times the Reynolds number, 1 minus y squared over h squared. So that's so I can multiply this by u, and I get that u equals gh over 2 rho u times the Reynolds number 1 minus y star over h squared. And one can go one step further and replace the Reynolds number as well. And the Reynolds number is given here, is rho uh over mu. So the rho u are going to simplify, there's one more h that comes in, and the mu at the denominator. And so that gives us gh squared over 2 mu 1 minus y squared over h squared. And that gives us the final results for this laminar flow in plane Poiseuille flow. So whichever you want to use, either you want to use it in dimensional form, but you sort of lose generality when you use the dimensional form. Or here, you use in non-dimensional form, you only have two parameters, the Reynolds number and your forcing term that you plugged in the beginning. Here you would have the forcing term g in dimensional form, there's h as well, and there's mu. So there's 3 parameters here, 2 parameters here, so whichever you choose. This non-dimensional form is always going to make you gain generality, but you might want to present your result in dimensional form at the end of the calculation.
In this video, we've considered one of the major examples of two-dimensional flows, which was plane Poiseuille flow. For this flow, we've decided to non-dimensionalize the flow and then solve for the laminar flow, the simplest flow realization that this configuration could yield. And we've presented the results both in dimensional and non-dimensional form. This concludes this video on plane Poiseuille flow.